In the previous video, we have talked about the problem statement of linear least square. In this video clip, I would like to give mathematical properties of the linear least square estimates. We're going to derive the solution. We're going to give you the properties and how to solve it by using existing software. So in this slide, we talk about the linear least square, and a very desirable property is that the solution is actually given in closed form. If you look at the cost objective of linear least square problem, the first thing to recognize is that, oh, it is an optimization problem and it is unconstrained. You don't have any restriction or we call it constraints on beta. You can choose arbitrary beta in Rn. Okay, and everyone knows from the calculus, from the basic optimization, that optimality condition for unconstrained problem is that the zero gradient conditions of the objective. So we take the derivative. Oh, sorry, typo. You take the derivative of the cost objective respect to optimization variable, which is beta here. And then, of course, I hope everyone review the calculus. Okay, this is composite function. If you have the two norms square, the derivative is of course 2x, right? But then you have a composite term. You take the two norm of F5 transformation. Okay, then this is to apply the chain rule. You get x transpose and y minus x beta and equates it to 0. Then when you look at this equation, you write it again, x transpose y, right, minus x transpose x beta equals 0. Then that turns out into the very important normal equation. Right. Now I would like you to take a look at this equation. Initially, your linear regression equation is a tall system. This is a tall system of, m equations. Your x is m by n. The normal equations is equivalent to the zero gradient condition. Now let's take a look at the dimension of this. Your x is m by n. Your x transpose is pink. Your x transpose is going to be pink. Pink is no longer here. Sitipak.
N by M.
M by M. So x transpose x is going to have size of
N by N.
N by N. The right hand side is going to be
N by 1.
N by 1. Beta is
N by 1.
All right. You see, it turns out to be a square system. The coefficient, like what we learned before, right? AX equals B. Now your A, which is X transpose X, is a square matrix. It's a square system now. All right. Of course, you know that when you have a square system, if the matrix A, which is X transpose X here, is invertible. If that assumption holds, you can just say, oh, my solution is unique and obtained by X transpose X inverse X transpose Y. This is the closed form solution of linear least square. Okay. The coefficients here that multiply with Y, this is the left inverse of X, because it is called a left inverse, because if you multiply x on the left hand side, what do you get? What do you get? Napat?
Identity matrix.
Identity matrix. If someone, in mathematical term, If A is the left inverse of B, it means that you multiply A with B on the left-hand side, and then it equals I. All right. Of course, there's a term called right inverse. It means that A is a right inverse of B. If you multiply A on the right-hand side of B, you get identity matrix. All right. Okay, now this is a nice result that, oh, actually I have a closed form. I don't need many advanced, tools in optimization. Initially, it seems like an optimization problem, but okay, at the end you have a closed form. Now we're going to discuss under what condition our X transpose X is invertible, right? Because the whole point relies on this assumption. Right, now it comes to the next property. So as we recall, when you have a matrix X that is rectangular, m by n, arbitrary, this is a known result for any matrix that the rank of X is less than the minimum between m and n. Okay, what is the rank of the matrix again? Can someone recall? Ping still here? Ping.
Yeah.
What is the rank?
Rank of matrix, right? Rank of matrix is the maximum of where here we can say the maximum of that when after we reduce Chulalongkorn form, and then we can see the number of I don't know how to say it. But
okay, Ping suggests that when you have a matrix X, you perform into echelon form, and probably you look at the number of leading ones. Is that what you're gonna say?
and then we can count it. Yeah, how much?
Yes, the number of the leading ones in the echelon form gives you the rank of the matrix X. Yes, okay, that's a procedure of determining the rank of X. There's going to be many ways. That is one of them. Can I say in short that the rank of X is the number of independent columns in X? All right. Rank of X is actually the dimension of the range of X, and that is the number of independent columns in X. Okay. If you forget this, review in linear algebra. Okay. So we have this identity. Rank of X is always bounded by the minimum between m and n. Okay. Number of rows, number of columns in X. If X is full rank for tall matrix, when you have a tall matrix, the minimum between these two guys is always what? It's going to be n, right? If you have a tall matrix, the minimum between m and n is actually n. Okay. So in that case, when we say X is full rank, it means the rank is at maximum. But then for tall matrix, rank of X is always less than n, right? For tall matrix. So when we say the rank, if X is full rank, rank of X is n. When rank of X is n, the null space of X is going to be 0 space. That is the rank nullity theorem. Okay, can someone state this for me? Rank nullity theorem says that rank of X plus dimension of the null space of X equals Toto, can you remember? Rank nullity theorem? Toto? Not here? Toto? You're gone?
I'm thinking.
Okay.
Rank of X plus number of no value of X will be equal to the n minimum between m or n.
N is equal to the dimension. Is equals to the number of columns in X. Okay. Again, review. All right. So from this theorem, you see that so once the rank of X is n, the null space of X must be 0 space. And what's the definition of the null space? It means that whenever the mapping, whenever the image, you know, of Z under the mapping X is 0, that is equivalent to say that that vector C must be 0 itself. Okay, now under this assumption, we're gonna explore. All right. First, you recognize that X transpose X is always positive semi-definite for any X, because this is quadratic form in X. All right. But then, if X is full rank, we can show that this guy is actually, I mean, is even stronger, is positive definite. Why? Because we can see that, okay, if you perform by the definition of positive definite matrix, you come up with a quadratic form in Z using X transpose ZX. But then you know that these can be written as the norm square of X times Z. All right? But because, of course, if you look at this quantity, you want to, if you want to examine whether this X transpose X is positive definite or not, you want to explore whether it is positive or not, right? Then we can conclude from the previous result that because the null space of X is 0 space, so this quantity must be positive for all non-zero Z. So that is the conclusion. The conclusion is what? If X is full rank of X is n, null space is 0 space, the quadratic form, you know, using X transpose X is always positive for non-zero Z. Then what happened? X transpose X is positive definite. It means that it is invertible. And that is the results you use that in concluding the closed form. So when X is full rank, X transpose X is invertible, which this term exists, then your least square solution has a closed form like this. That is the conclusion. Okay. We have geometric interpretation of a least square problem in term that can be associated with orthogonal projection. So take a look at this. All right, we have a vector y. We have a vector y. You have vector x1, x2 in the blue arrows, in the blue vectors. Okay. Whenever you have a blue, whenever you have x1, two vectors, you can, of course, the span of these two vectors, the span, right? Span is a set, right? Span of these two vectors becomes a hyperplane, right? So finding, using a relationship, a linear relationship, y equals y beta 1 x1 plus beta 2 x2 is actually the same as saying that you want to estimate y, you know, that is a vector in a hyperplane spanned by x1 and x2. So the red vector, which is given by the least square solution, when you use x times beta least square solution, suppose that the optimum coefficient is 2 and 1, right? So it is actually the estimate of the vector y. How is the estimate that given by a vector on the hyperplane spanned by x1 and x2. Okay. Now we can show that actually the linear least square solution is the orthogonal projection of y onto the range of x. Okay, so recall the definition of projection. So you have you have a vector y, all right, and then look at the pink area, all right. The pink area is the range of x. The range of x is always spanned by the column vectors in x, which is here in this example is x1 and x2, all right. So you project it into this plane. It is called orthogonal projection because of this principle that the error between the original vector and the projected vector py. So this is the error vector is orthogonal to the space Rx. Is orthogonal to the subspace that you project into. Okay, and because the subspace Rx has basis vectors of x1 and x2, you can also say that the error vector is orthogonal to py as well, because py here, okay, we're gonna show later what is p, but for now py means that projected vector, projection of y onto the subspace of Rx. Okay. All right. If you look at the two norm, the two norm residual y minus x beta two norm is a distance between the original y to the vector that is spanned by x1 dot xn. So when you replace this beta with a linear least square solution, it gives you the best linear combination of xn that is closest to y. The best, what do you mean by the best? It is the best because we can show that the best means that the projection here, x beta rs, is the orthogonal projection of y to the range of x. Okay. Now, so we're going to recall what orthogonal projection is. Orthogonal projection is the following, as I mentioned previously. Okay. It is called the orthogonal projection when suppose py is the projected vector onto a subspace of your interest. Here now is the range of x. Okay. Why the subspace of interest is a range space of x? Because when you use linear least square, this is your y hat, right? Y hat equals to x beta. Y hat is a linear combination of x1 dot xn. So when y hat is a linear combination of column vectors in x, now I use notation that my x1, x2, and xn is actually columns in x. So you can say that my y hat is in the range of x. Okay. Then orthogonal projection says whenever you have a subspace of interest that you're going to project into, you have a projected vector, the error, which is y minus py, must be orthogonal to all the vectors in Rx. But because the basis sets of our range of x is actually columns in x, so it means that xk must be orthogonal to the error for all k. Okay, the optimal residual is orthogonal to any vector in Rx. Okay, so the projected vector gives the best approximation for any y hat in range of x. It means that if you come up with another y hat that is also lies in this range space, this is another y hat, your projected vector will give the minimum residual. Is always less than the residual obtained by other y hat. Okay, the second bullet can be proved, this inequality can be proved, but I'm gonna leave it as an exercise. Okay, which means For if you use another y hat that also lies in the range space of X, the residual here, y minus y hat, doesn't satisfy orthogonal condition. It's not perpendicular to any vectors in range of X. Okay. Next, from the orthogonality condition, which is xk transpose y minus py equals 0. Okay, now I'm gonna write it into xk transpose y equal xk transpose py. But remember, the principles of the orthogonal projection is that your py, the projected vector here, must be a vector in the range of X. So if your py is in the range of X, your py must be written by a linear combination of column vectors in Rx. So I'm going to put back this expression of py back into this equation. Okay, so now we have formed this equation for all k from 1 to n. Now I'm gonna iterate this equation from 1 to n. So the first equation, x1 transpose y, all right? And then you're gonna have inner product x1 transpose x, x1 transpose x2, and so on. And when you keep repeating this, you have n equations. These n equations, of course, I want you to notice is that if you have x, right, that partition into xn, x1, xn, as I mentioned before, what is x transpose? It's going to be x transpose, x1 transpose, x2 transpose, xn transpose, right? So if you multiply with x transpose x is actually the matrix given here, right? And of course, x transpose y, which is x1 transpose, x2 transpose, xn transpose times y, is actually the vector on the left-hand side. Which means the condition we derive here from orthogonal projection condition actually turns out to be the same as the normal equation. So when you get the linear least square and multiply with x, that is the projected vector. That is the projected vector given from the orthogonal condition. So your P, this is called projection vector. It is called projection vector because when you multiply P on the original vector y, it gives you the orthogonal projection of y onto the range of x. So your P is this matrix. Okay, and of course, provided that X is full rank, so that this inverse form exists. Okay, I hope everyone recall and review what projection vector is in general, so that you can review, you can confirm, verify that this expression of P in the context of projection y onto the range of X satisfy the orthogonal projection property, that is P squared equals P is symmetric. You can verify it real quick. Oh, P squared, compute the P squared, and then check that it is actually equals to P. We're gonna come back later to this P several times. Okay. It's gonna have some other properties. For example, I minus P must be positive semi-definite. Okay, please check. All right. Okay, at the end, I would like to end the video by giving some information about how to solve it numerically, okay, just by using some library. So recall to the normal equations that actually in the format of ax equals b, okay. So when you solve normal equation, your x transpose x, which is a row of the matrix A here, your x transpose x is positive definite matrix if x is full rank. So one way is to factorize x transpose x into Cholesky factor L transpose, and Cholesky factor has the property that it is lower triangular. So when you factor this, okay, suppose I say that the right hand side is beta, right? So you can, when you solve it, you can think of this as z first, and then you solve LZ equals b, right? When you solve linear equation in triangular form, solving this is going to be cheaper in the sense that because L is lower triangular, so you can use backward substitution. We have this discussion in the course of 507 numerical analysis. All right. So basically, I'm telling that solving linear system with coefficient triangular is going to be cheaper than solving a general linear equation. So once you get Z, once you get C, you can form L transpose beta equals Z, and that's another triangular system. So you can solve beta again. All right, that's one way. Another way is to use the QR factorization, and that's actually the main the common practice here to solve least square using QR. We're going to explain later. But let me point out to some library commands. For MATLAB, you can use backslash. Okay, so it's left divide, which means that as from our numerical examples, like recall to the engineering application that we see before, right? Once we have formed a vector equation x beta equals y, okay, you have x and y, then you can just use the command in MATLAB, all right, x backslash y. Okay, so that's one way. And in Python, you can use SciPy, the least square library, then that you can get beta hat. But because the linear least square is a very common tool, it's used in many applications, and the results has some statistical property and so on. So people have developed some statistical tools as well. It's fit LM. So this gonna return the whole model. It returns some statistics as well, like return the p-values, return the confidence interval of the estimate, return a lot of things, return the y-hat. Okay, so you actually don't need to compute anything. But the command just do everything for you. So, and in Python, there's scikit-learn and the linear regression. So let me remind again that, of course, you can use these two to solve the closed form that we derived. This is for analysis purpose. We're going to use these to analyze further about the property of the least square solution. So you don't actually type x transpose x and then put the inverse and then times x transpose times y. This is not actually the way you compute the least square solution on the computer language. Okay, so of course in the homework exercise we're gonna give you problems. You formulate into the linear least square, and you can use this library to compute the estimate. The whole point of linear least square is not about computing. The computing part is very easy, right? But then the formulation part is more important. So I think that this is all for the second video clip of the linear least square. In the next video clip, we're going to explain about QR factorization.